Well, greetings, mathletes, and welcome back. I've got good news for you today. We actually get to start some trig. We've done a little review now, and we're going to be able to actually start talking about some angles and things like that. And actually, we're going to relate that to circles and a couple other things. And we're basically setting the foundation for everything we're going to be working on in trig. So let's go ahead and get started. Let's see here. Let's go do that. Now I want to start with a circle here. So let's see. I don't know, my drawing pad. I'm so much better at this on a whiteboard. We'll see how it goes. Try one more time. Something like that. That looks circular enough. Okay, so first of all, we need to start by talking about something called standard position. Much of the time when we talk about angles, we are going to be measuring them from what's called standard position. So in any case, if you go ahead and center a circle at the origin, right? So this is your x coordinate, this is your y coordinate. Standard position is any angle is in standard position if one side of it lays on the positive side of the x-axis, the vertex of the angle sits right on top of the origin, and then the other piece of the angle can go any direction, right? And so we have an angle here. Now there's a few other things too. This is an angle in standard position. Notice that it seems like the angle moves this direction, and that's because it does. So with angles counterclockwise, is a positive rotation. So any angles we measure that go counterclockwise like this, we're going to be considering those positive angles. If, for some weird reason, your angle is being measured this way, you actually you would write the measure of the angle in negative numbers. Right? So now we have negative and positive angles, and it just depends on which direction you're turning, right? So we will be playing with some of that stuff here. Now, a couple other things. Let me go ahead and there we go. More definitions. Okay, so first of all, this circle has a radius here, right? And we're going to use r for our radius. This angle, now for angles we typically use Greek letters. That's not always the case, but there's a lot of time we use Greek letters as far as that goes. In this case, typically when we're talking about this, you use alpha, beta, or theta. Those are the three Greek letters that we use the most. So let me write these down here. So alpha, and I'm just going to, that is written alpha, and then there's beta, and that does have the tail on it like that. In fact, this is where we get the word alphabet from. Alpha, beta. It's like saying ABCs, right? But you're saying it in Greek. In the Greek alphabet, the actual next letter that pops up, it's alpha, beta, gamma, delta, epsilon, a few others. But just for the time being, this is theta. Those will be the ones we use the most. And right now, I'm going to be talking about angles in terms of theta. So this angle here is theta. And then up here, the length of this piece, right, the arc of the circle, we're going to use S for the arc length. Okay, so we've just labeled all these things, and basically what this is doing is it's going to give us a chance to actually to actually quantify some of this stuff and look at it in terms of equations. Now, up until today, I mean, unless you have some trig exposure already, you've always measured angles in degrees, right? And one full rotation is 360 degrees. We know that. So now, if I want an angle measurement in, excuse me, actually I hadn't even talked about it. There's a different angle measurement that we need to use, and these are called radians. Okay, so radians they're a completely different quantity. What we're going to do is we're going to look at how radians work, um, and then excuse me, and then figure out how to convert back and forth between degrees and radians. So first of all, um, radians, basically, if you want the radian measure of any angle, right? The angle's measured in terms of the radius and the arc length. And you can see I could change the angle if I kept the arc length the same but made the radius bigger, it would shorten the angle. If I lengthen the arc, right? If I move this way with this angle, it would make the radian measure or the angle measure bigger. So it turns out that if you want the radians, it is the length of the arc divided by the radius of the arc, right? Or the radius of the circle. Okay. Now, typically, well, actually, let's go ahead and do this. I have another thing I want to show you real quick. So here's a little demonstration. This is a little model here of looking at these three quantities, right? If I wanted to have 1 radian is set up on this circle so that I take 1 radius, and I wish I could draw on here. Let's see if I can. Right, I'm going to take a radius, this thing right here, and I'm going to take that distance and I'm going to measure it up here around that arc. Now, I can't draw the curved line there. I need a circle to do that. But if I could flatten that line down so that 1 radius wraps around the circle, wherever that other point is the angle it makes is 1 radian. Okay, so basically, to have 1 radian, let's make sure I have this here. Right, I want an angle so that whatever this radius is also the arc length. Right, that's what we want. And then this angle here would be 1 radian. Okay, now, typically when you write radians, when you use that as a unit, technically radians don't have a unit because the units cancel out. If you've done any dimensional analysis, you can actually see it cancel out as you work on this stuff. But oftentimes when we talk about 1 radian, we'd say one rad or something like that. Okay, so hang on, let me get some of this stuff off of here. So right now what we're doing more than anything else is just laying down some definitions and things. Okay, now we're going to find out how to convert between radians and degrees. Okay, so first off, well, we need to know if we knew how many radians were in 1 rotation, we could compare that with 360 degrees and see how they line up, right? And so that's what we need to figure out. And since this is done by arc length, we know that the full arc length of 1 revolution is going to be the circumference. And the circumference is equal to 2 times pi times the radius, right? Okay, well, the angle measure in radians is the arc length divided by the radius. Well, if we're talking about a full rotation, the arc length is the full circumference. So S is 2 pi r. And if I'm dividing that by r, those cancel out. And so I have 2 pi radians in one rotation. And what that means is that 2 pi is equal to 360 degrees. In fact, we can write 2 pi radians just so we know it's an angle. So 2 pi is equal to 360 degrees. And if I divide both sides by 2, I know that pi is equal to 180 degrees, right? And so that's half a rotation. So if I do half a rotation, right, if I rotate from, let's say I need another color. If I rotate from here to here, I have rotated pi radians, right? So if I go all the way around, it's 2 pi radians. And so this is going to give us our conversion factor. If I'm given something, let's see here. Let's put something in degrees first. Let's say I have 60 degrees, and I want to convert that to radians. Well, what I'm going to do is I'm going to use this pi over 180. Since these two things are equal, pi over 180 is equal to 1, and 180 over pi, degrees, is equal to 1. And so these are going to be our two conversion factors. What I want to do is figure out which one's going to cancel out the unit I have. I have degrees here. I want radians. So I'm putting the radians on top. I have pi radians. And I'm going to put the degrees on the bottom here because degrees cancel degrees, right? So I want one on top, one on bottom. And then I can reduce this. So that goes into 60 once, and that 60 goes into 183 times. And if I multiply what's left, I find that 60 degrees is equal to pi over 3 radians, right? This is something we're going to be dealing with a lot. In fact, there's going to come a point very soon where we just kind of stop talking about degrees, and we deal almost exclusively with radians. This class, we still bounce back and forth between the two, but what do you call it? As you climb the ladder, pre-calculus, calculus, by the time you get to calculus, there's very few degrees that you see anymore. It's almost all done in radians. So that's something good to know. So yeah, this is the conversion back and forth. Let's go ahead and look at another one here. Okay, so let's say I have, 315 degrees, and I want to change that to radians. And so it's the same thing. I know I have pi radians on top. I have 180 degrees on the bottom. Degrees cancel degrees. Let's see here. Let's see how we can reduce this down here. Let's see. 3 goes into both of them. I'll start there. So that makes that a 60. And 3 goes in here. 103 times? Is that right? 3 goes in 105 times. I'm dividing wrong. Right? So now I have, I'm just going to write down what I have left. 105 pi over 60. So I can keep dividing down. I'm going to divide by 5 this time. That will give me 21 pi over 12. And 3 goes into both of those. So this is now 7 pi over 4. Right? So this would be 7 pi over 4 radians. And RAD is the abbreviation for radians, but when you're writing radians, you actually don't have to write the unit. That's a little extra thing, and what it does is it just gives the reader a context to know that what we're talking about is an angle in this case. Okay, so let's see if we can go the other direction, because oftentimes you'll see things like 2 pi over 3 radians, and you want to go to degrees, right? So let's go ahead and take a look here. I'm just going to rewrite this so we have some room to work. Now, remembering Before we multiplied by pi over 180 because I put degrees on the bottom because that's what I was trying to get rid of. Well, now we're trying to get rid of radians. So I'm going to put radians on the bottom. And so I'm going to multiply 180 degrees over pi times 2 pi over 3. And then we'll just start canceling things out and see what happens. So let's see, pi cancels with pi. 3 will cancel with 180 to leave 60. And notice I still have the degrees. I didn't have any other degrees to cancel out, so the answer has to be in degrees. 2 times 60 is 120. And so we get 120 degrees. So 2 pi over 3 is 120 degrees. So it basically boils down to this. If I'm going from degrees to radians, right, I multiply by pi over 180. If I'm going radians to degrees, I multiply by 180 over pi. And I guess I should probably make these degrees too, because that is important, right? And so that way you can keep track of what you're trying to get rid of and make sure that that thing is on the bottom, right? So the thing you want, you put on the top. The thing you're trying to get rid of, you put on the bottom. And it works like that every single time. Okay, so we've talked about standard position, we've talked about radians and how to convert back and forth between radians and degrees. Let's see. Okay, so the next thing we need to talk about are going to be coterminal angles. So let's go ahead and clear this off. Okay, so the idea of coterminal angles. Oh, here we go again. Let's try this. Okay, so coterminal angles are angles that can actually be treated as equivalent angles. You in problems and things like that, for the most part, you can treat them as the same angle, even though they're not technically the same angle. They look like the same angle. And you'll notice in here, in coterminal, you see the word terminal, right? And what does the word terminal mean? It means you're gonna die, Mr. Brian. I suppose in some cases it means that, but no, in this case it's talking about it ending, right? And not dying. We don't want to get all morose here. Oh, good, because it seemed like that would be dangerous. Now we're keeping everything safe here, okay? Okay, so let's actually look at this. So let's say I have an angle here. In fact, let's switch the colors. Oof. Wow. Okay, I'm going to try that one more time. Actually, I wonder if this works. Let's try this. Yeah, that's one of the best circles I've ever drawn. And let's draw another one. Oh, that's not a circle, is it? Let's try another one. There we go. Okay, so we have two circles here. And let's put them in standard position. Too many controls. There we go. Okay, so here's the first angle I want to look at. It arcs through here and goes to right there, right? And so I have an angle measure that I can clearly see. Now over here, right? This time I'm going to add an extra 360 degrees to this angle, and we'll take a look at it. And what we see is that, okay, so that means I go around once. There's my 360 degrees, or 2 pi, right? And then the angle ends at the same place, right? So one of them went around once and then completed the angle. The other one only just went straight to the stopping point and stopped there. But you'll notice they're at the same point, right? All the measurements here will be identical. The only difference is this one has an extra rotation in it. So coterminal angles are different by a multiple of 360 degrees, or 2 pi, right? And so we're going to have to get used to doing some arithmetic with 2 pi because, well, I mean, we're going to be dealing with radians a lot, and most of the time, radian measures are fractions. So we will have to get used to doing a lot of that. Okay, and so basically what this is saying is that they're off by some number of rotations. I could have put one more rotation in here, right? This could have gone around 3 times before it stopped here. It could have gone around 5 times before it stopped here. It's about the stopping point. So if they have the same stopping point, so they stop and the same smallest angle here is identical, then those two angles are coterminal. Okay, so let's go ahead and do this. And maybe I should just start with the shapes. Nah, I'll actually just write this down. So, oh yeah. If I want to find an angle coterminal to 840 degrees. In fact, let's give the angle a name. So an angle theta, they do this a lot where they tell you what the variable is you're going to be using. So we find an angle theta coterminal to 480 degrees such that theta falls between 0 and 360 degrees, right? So somewhere between, I want it, basically it could equal 0. It doesn't equal 360 because 360 is coterminal with 0. We don't want two choices for the same thing. So basically it works like this. If you want to get this thing between 0 and 360, well, this thing is way over 360 right now. So what I'm going to do is I'm going to keep subtracting 360s from this until I get something between 0 and 360. So if I have 840 and I subtract 360 once, I get 480. Well, that's still too big, right? That's bigger than 360 still. So I'll subtract another 360 out of this, and I get 120. 120 is between 0 and 360. So so theta in this case would equal 120 degrees, right? Now, sometimes you're given, and let's just go ahead and do a very similar problem, but so find an angle coterminal to negative 72 degrees. Okay, so now we have something negative. Well, again, we need it between 0 and 360. So what what do you think I'm going to do here? Excuse me. Could you add 360, Mr. Bryant? Yeah, you could add 360. Let's just see what happens. So I have negative 72 plus 360, which is the same as subtracting 72 from 360. Right? So if we go through and do all this business, let's see, I get 8 there. That gives me 8. That gives me 2. So I get 288 degrees, and that is between 0 and 360 now. And so 288 degrees is the same as negative 72. And basically what we did was this, right? If I have my thing in standard position here, negative 72 would have been down here. Because it's negative, that means it's going this way. The coterminal angle goes around this direction, 288 degrees. And they end up at the same place. So as long as your angles end up at the same place, they are coterminal. Okay, so let's go ahead, clear that out. Mr. Bryan, I'm sorry to interrupt. Um, are we going to have to do that in radians too? Because you said we're going to use that a lot. I'm so glad you asked that. It was like you read my mind almost. Um, no, yeah, we will definitely have to do these in radians also. As a matter of fact, that's what this example is going to be. So, buckle up and then let's take a look at it. All right, I'm ready to go. Cool, then let's do this. Okay. Um, yeah, so let's say we want to find, oh yeah, let's find my pencil. Okay, let's try it again. So we want to find an angle theta coterminal with 17 pi over 3 such that, oops, 0 is less than or equal to theta, which is less than, and well, now we can't use 360 anymore, so what we use instead is 2 pi, right? Okay, so we want to take this and we need to scale it down to a number between 0 and 2 pi. And so, well, it's really it's kind of hard to see if this is 2 pi or not. But if we were to convert this to a whole number or to a mixed number, 17 thirds would be 5 and 2/3, right? So it's well over 2 pi. So it's just a matter of subtracting this stuff out. Now, here's one of the things I like to do. If I'm dealing with something that's a fraction and I got a denominator here, the first thing I'm going to do is convert 2 pi to have this denominator, right? I want this to have a denominator of 3, and if I convert 2 to having a denominator of 3, it ends up being 6 pi over 3, right? If I reduce that, I get back to 2 pi. So that means that I can start working with this thing. I have 17 pi over 3, and basically I'm going to keep subtracting 6 pi over 3 out of it till I get something that's less than 6 pi over 3. So if I keep doing that, in fact, if I just look at this, all I'm going to end up doing is subtracting the numerators. So let's just see how long it takes to get to how long I can subtract 6's before I get, what do you call it? I can't talk right now. Before I get something that's less than 6, right? So if I have 17 pi minus 6 pi, I get 11 pi, right? If I subtract another, well, I'll write the whole thing. Another 6 pi over 3, that gives me 5 pi over 3, and 5 pi over 3 is in fact less than 6 pi over 3. And so that coterminal angle theta is equal to, I almost put less than, let's try it again, is equal to 5 pi over 3, right? And that is strictly because of the fact that that we're manipulating radians now instead of degrees. So you do have to deal with the fractions, but you can always find a common denominator for that 2 pi and just keep subtracting numerators out to make it a little bit easier. Because you notice really the only actual subtraction I was doing was subtracting 6 when I did this whole stuff, because the denominators stay the same. So any way you can find to make the arithmetic a little quicker, by all means do it. Some calculators will give you answers in terms of pi, some will not. Some will only give you the decimal. So, pay attention to what kind of calculator you have as well. Okay, so let's go ahead and clear this off. And I actually want to take a look here at finding arc length, because this finding the arc length will lead us directly into our discussion of angular and linear velocities. So let's go ahead and take a look at this. So we had decided, if we're talking about radians, that theta is equal to the arc length divided by the radius, right? And remember, s is the arc length. So if I want to work on finding a formula for the arc length, well, I just need to get s by itself. And if I multiply both sides by r, I find that s is equal to theta times r, or r times theta. It just depends on, whatever you're dealing with. Different books talk about it different ways. Yeah, so we have theta r here, which is actually a really convenient formula. So if I have a circle, right, and that circle's radius, right, so wherever it crosses the x-axis is actually going to tell you the radius if this circle is centered on the origin. Let's say this radius is 80 feet, right? And I'm going to measure out an angle on this. Let's switch colors so I can see. Right? That's this far. And let's say what I'm told, I'll call this angle theta here. And this particular angle, let's see here, what goodness can we cook up here? Yeah, let's say that this angle is 2 pi over 3. That was actually one we did earlier. If you remember, we came out that was 120 degrees, right? Okay, so the angle's 2 pi over 3. The radius is 80 feet. So if we want to know the arc length here, how long this particular arc is, well, I can use this formula, right? We know theta, we know r, so that means s is going to be 2 pi over 3 times 80 feet, right? Now, just looking at this and simplifying this, 3 doesn't go into 80 evenly, right? So there's no way to simplify that. So this ends up being that the arc length is 160 pi over 3 feet, right? Now that is an exact answer, right? That's a perfectly exact answer because I'm using the symbol for pi instead of the decimal approximation. So this is not an approximation. So if you want a decimal approximation, because that's actually easier to picture those lengths in your head, you can go ahead and use your calculator. Calculator, there we go. So let's see what we get here. We have 160 times pi divided by 3 equals 167.55 feet, right? And that actually makes sense. Right, this is closing in on 2 radians, and if it's 1 radian, then the distance here that it covered would be 1 radius. So this is going, just the distance it's covering is just a little bit more than 2 radii, because 1 radius is 80 feet, right? And so this is just a little bit more than 2, and so it makes sense. Right, so these are the 2 different ways that you can represent that, but that is one of the ways that you find arc length. Okay, it's a pretty good app on that calculator, isn't it? Okay, so we want to remember that. Oops, that is not. Let's try this again. Control. There we go. Sooner or later, I'm going to learn these controls. Okay, so we noted that. Got that. Let's change that. S is equal to theta times r. We also know, let's see, we decided, and that actually came from this, S over r is equal to theta. Now, there's a couple of rates that we need to talk about. One is the linear speed, and I kind of don't like the fact that they're using speed. Speed is the absolute value of velocity. And they use v here, and there's no absolute value, but they're calling it speed. So we're just going to go with it for now. It really is a velocity. If I'm talking about a velocity, remember velocity is in miles per hour, feet per second, things like that. It's a unit of distance divided by a unit of time. And if we're talking about the linear velocity of something that is on a circle, right? We're talking about how much actual distance they cover. And you notice if I'm on the surface of a circle like this, the distance I cover is an arc length. So instead of a distance divided by a time, we write it as an arc length. S. Oh, let me change that to black so it matches. It's an arc length divided by a time, right? And then there is angular velocity. And that's a rotation speed, like how many revolutions. You hear this all the time, RPMs, revolutions per minute, right? It's how many, it has to do with how far the angle goes in a certain amount of time. Angular velocity, we use the Greek letter omega, which looks just like a W. It looks like a lowercase w. I like to put the little tail on it so I know I'm not using a W, but angular velocity is use the Greek letter omega, and that is in radians per second. Oh, I'm sorry. I'm going to use T for time. So that's kind of interesting there. Now, there's something else that we can use to tie these two things together, which is kind of interesting. And this only works if we're talking about radians, right? So theta is radians. Because radians does a real good job of connecting distances with angles. Okay, so if I look at my formula for linear velocity, right? Well, we already know that S is equal to theta times R, or R times theta. So if I substitute theta times R for S, I can write this, right? So you can actually compute the formula with the angle, the radius, and the amount of time. But you'll notice something else in here. I have a quantity of theta over t. This is actually the same as theta over t times r. And if you remember, theta over t is the angular velocity. So if you want the linear velocity, you take the angular velocity and multiply it by the radius. And so that's another really nice formula to add here, that the linear velocity is equal to the angular velocity times the radius. So if you know how fast it's going around, and you know the radius, or you know how fast it's turning, and you know the radius of the circle, you can see how far it's gone, right? It's actually kind of a nice little deal there. And so let's see if we can find an example of this. So let's go ahead and clear that off. So here's a handy dandy little example. Okay, so while on vacation, Candace decided to visit an old water wheel that had been restored for tourists. Okay, the tour guide stated, should have paid more attention to my English classes. Let's try this again. The tour guide stated that the water wheel had a radius of 12 feet, and when it was in full operation, it could spin fast enough to complete 100 revolutions in just 5 minutes. Candace thought about it for a minute, and then she wondered what the speed of the water was going over the wheel. If it was in full operation, how fast was it moving? And so we want to give our answers in feet per minute here. And typically there's two forms of the answers when it comes to this. There's the exact form, which, quite honestly, since we're talking about a linear velocity, but in terms of circular motion, there's probably going to be some form of pi showing up in your answer. So, um, excuse me. First thing I want to think about is, what does this actually look like? So I'm just going to kind of sketch a picture here. So this is my water wheel. And if you don't know how a water wheel works, there's usually some river or something where, there's two levels, and you have an upper level up here, and there's usually some sort of trough that's feeding the water this. Oh, I should make it blue. It's water, right? It's feeding the water this way, and it flows over the water wheel, causing the water wheel to spin at the same rate as the water, as the water flows, right? So that's the idea. That's what a water wheel does. And so what Candace is trying to figure out is, this water going over the edge as it's turning and falling, how fast is that water going to get this thing going at what do you call it, 100 revolutions in just 5 minutes, right? And so that's what we're trying to figure out. And if we're figuring out how how fast it's going around here, that's actually a linear velocity, right? So that's a velocity, not an angular velocity. So knowing that it's a linear velocity, we had two formulas for that. We had linear velocity is equal to arc length divided by time. So it's a distance divided by a time. And then the other one we had was in terms of, what do you call it? The angular momentum. If I take the angular momentum and multiply it by the radius, then I get the linear velocity. So those were the two things that we had there. Now, if we look at what we have, I'm given 12 feet as a radius. Well, that's this piece, isn't it? That's our R. And then I'm told it does 100 revolutions in 5 minutes. Well, that is a angle. A revolution is an angle. It's a 360 degree or a 2 pi angle, depending on how you want to look at it. And 5 minutes is a time. And so I can take 100 revolutions per 5 minutes, and I can simplify that down to 20 revolutions per minute. Now, in fact, let's write it this way. Okay, and that is an angular speed. That's an angular velocity. But if you remember, we can't deal with revolutions. We have to deal with what do you call it? We have to deal with radians if we're going to do this. So I have to switch these 20 revolutions to radians. Now, we know we're trying to get rid of revolutions, so I'm going to put that at the bottom of my factor. And what I want is radians, and 1 revolution is equal to 2 pi radians. And so the revolutions cancel, and I end up with 40 pi radians per minute. Now, typically you do write the radians when you're talking about a rate, just so it's real clear that these are radians, but technically you don't have to, right? 40 pi per minute is actually the units that it is. Okay, so that's our omega, right? Omega would be 40 pi radians per minute. And so we can just plug things in. So I can drop in 40 pi times the radius, which is 12. And so that means I have 480 pi. Yeah, and it would be, let's see here, it would actually be feet now because the radius is in feet. So it's feet per minute. Now that would be the exact answer, right? It would be 40 pi feet per minute. That's right there. You may be asked for a decimal as well, in which case you need to plug it into the old handy dandy magic calculator box. 480, and usually there's a button for pi that'll take it out quite a few decimal places. And so if I plug it into the calculator, 480 pi comes out to 1,507.96 feet per minute, right? And that's our answer. So both of these are correct answers. It's just a matter of which one you're being asked for. If you're asked for a decimal, it'll tell you where to round it, because typically once you have pi involved, the decimal never ends. Um, and if it's asking you for an exact answer, that's when you leave it in terms of pi, right? You don't simplify stuff. Those are the ones that leave the fractions in the answer. But yeah, both of these are correct answers. And so hopefully that makes things a little more clear. Now, I can't do let me do this first. I can't go through and do every kind of example as we go through here. So what I encourage you to do is work on these, work on the homework, right? You have homework and all that kind of good stuff. Come to me and talk to me if you have issues. I have tons of office hours, and I'm available almost all the time. So please talk to me. And in any case, so that ends this particular lecture. And so until next time, keep your pencils and your wits sharp.